I challenged myself to code multiple maze generation and solving algorithms in both 2D and 3D to see which ones are the fastest at solving them. At the end, I'll attempt to build the biggest maze in the world without crashing my computer. So first we need to figure out how to create the mazes that we want to solve. A maze is basically a grid made of cells, and each cell has a bitmap representing the 4 walls around it. The first bit is the top wall, the second is the right wall, the third is the bottom wall, and the fourth is the left wall. To remove a wall between two cells, we just set the corresponding bits in both cells to 0. To let the computer design a maze for us, we can use an algorithm. One of the simplest ways is using a depth first search, DFS in short. DFS moves as far as it can in one direction, removing walls along the way. When it can't move any further, it backtracks until it finds another path to explore. When it's done, we get a perfect maze. A perfect maze is one where all cells are connected without any loops or isolated sections. In graph theory terms, it's called a connected acyclic graph. I also created a graph visualizer that makes it easier to see the tree-like structure underlying the maze. There are many other different maze generation algorithms, each producing unique patterns. One of the most visually interesting is the recursive division algorithm, which repeatedly splits the space into 2 smaller areas with a single open pathway. Watching a maze being generated this way is pretty mesmerizing. These algorithms scale well to larger mazes, though generation takes longer as the maze grows. That will become a real challenge when we try to create the enormous maze at the end. Now let's move on to solving our newly generated mazes. There are many ways to tackle a maze. The simplest and least efficient method is a random walker, which moves randomly and hopes to stumble upon the goal. A slightly smarter approach is the wall follower, which continuously follows the left or right wall. On a perfect maze, this method is guaranteed to eventually reach the exit. A more practical approach is to use depth first search again. It works just like the DFS used for maze generation, but this time it starts at the maze starting cell. DFS is effective, but in mazes with loops, it doesn't guarantee the shortest path. Dijkstra's algorithm treats each cell as a node and always expands the closest unvisited cell from the start, updating distances along the way. Once it reaches the exit, the recorded path is guaranteed to be the shortest. A-star is very similar to Dijkstra, but it adds a heuristic to prioritize cells that seem closer to the goal. By combining the actual distance traveled with this estimate, it usually finds the shortest path faster and still guarantees optimal results. Now let's race these algorithms on 3 progressively larger mazes to see which one is the fastest. The first maze is a 100 by 100 grid, pretty small, right? And yet the random walker needed 11.5 seconds to solve it. That's painfully slow. Now let's compare that to the actual algorithms. Depth first search finished in just 21.8 milliseconds. A-star did even better, taking 13.8 milliseconds. Breadth first search, a similar algorithm to depth first search, came in at 12.2 milliseconds, but the real surprise? The wall follower solved it in only 4 milliseconds. Now things get interesting. The next maze is 25 times bigger, a massive 500 by 500, and the random walker, it never finished, not even close, but the other algorithms stepped up to the challenge. Here are their times. Finally, we move to the real monster, a 2500 by 2500 maze. That sounds enormous, and it is, but believe it or not, it's only 0.58% the size of the world's largest maze, which measures a staggering 32,768 by 32,768 cells. That's millions upon millions of cells. So now the big question is, who wins this race and earns the right to solve the world's largest maze? And the winner of this race is the wall follower. But wait, it doesn't give us the actual shortest path to the maze. Okay, the actual winner is the breadth first search algorithm. Congratulations, you'll be solving the world's largest maze. I noticed by removing a few random walls, we create alternate paths in the maze. This means it's no longer a perfect maze, but solvers can now take shortcuts. You will notice that the depth-first search algorithm, shown in green, sometimes ends up taking much longer routes, while A*, shown in red, finds a faster path. Fun fact, Google Maps also uses the A* algorithm to calculate the quickest route between two locations. Okay, 2D is getting kind of boring. Let's add some perspective to make the maze more interesting. That's right, we're moving into the third dimension. In 3D, each cell doesn't just have 4 neighbors, but 6. Despite this extra complexity, our maze generation and solving algorithms work exactly the same way as in 2D. The concepts we've learned so far carry over seamlessly. In 2D, each cell was just 4 lines representing the walls. In 3D, things get a bit more complex. Each cell is now a cube with 8 corners. The challenge is projecting these 3D vertices onto a 2D screen. To achieve this, we just use a little bit of magic, math. We solve this using matrices. In fact, I have 2 different projection matrices, one for the orthographic projection and one for the perspective projection. If we also want to scale, rotate or translate the cube, we simply create matrices for each operation, multiply them together, and boom, we get the final 3D rendering. To draw the walls of the cells, we connect the appropriate vertices with lines, forming the cube's edges. If we increase the maze to a 5x5x5 cube, we expand the single flat layer into a full 3-dimensional structure. This dramatically increases the number of cells and possible paths, making the search space much larger and the pathfinding problem more complex. To help visualize the maze, I also created the 3D graph visualization. I really like how this one looks. It gives a clear sense of the maze structure and the connections between cells. But why stop at 5x5x5? Let's see how far we can push this before my computer starts begging for mercy. At 10x10x10, the maze still runs kind of smoothly, the 3D structure is getting dense, but my PC is holding on. At 15x15x15, that's 3375 cells, things are getting serious. The frame rate drops noticeably, hovering around 10 FPS. And finally, at 20x20x20, a staggering 8000 cells, my computer is barely holding on. The frame rate has crashed to about 1 to 2 FPS, each frame taking nearly a second to render. The maze just looks like a solid block of cells. At this point my CPU is maxed out and I can smell something burning. I think this is as far as we can go in real-time 3D rendering with a CPU. After pushing my computer to its limits with 3D rendering, I started wondering, what if we skip the real-time visualization and just focus on generating an image? Not in 3D, but back in 2D land, and make it absolutely massive. How big can we go before my computer actually explodes? The goal is simple, create the biggest maze in the world. But to get there, I'll need to overcome several serious challenges. First, the algorithms need to be extremely efficient. What worked for smaller mazes won't cut it here. Every operation counts when you're dealing with billions of cells. Then there's memory usage. Storing a maze this large in RAM requires careful optimization. I had to rethink how the maze data is structured to avoid running out of memory mid-generation. The program sometimes needed multiple gigabytes of RAM to hold all the data. Next up, file size. Saving an image of a maze this enormous creates a file so large that most programs can't even open it. I had to experiment with compression and file formats to make it manageable. In the end, I used the TIFF file format. And of course, there's generation time. Creating a maze of this scale doesn't happen in seconds or minutes, it takes hours. But if I can pull this off, the reward is worth it. I'll be the creator of the biggest maze in the world. Let's see how far we can push this. For generation, I used the depth-first search algorithm, and for solving, I used the breadth-first search algorithm, the winner of our race before. For the final image, I chose a simple 4-color palette. Black for empty spaces, white for walls, green for the solution path, and red for the start and end cells. Then I gave it a try. but it immediately crashed after generating the maze and attempting to solve it. I ran out of memory. Okay, let me close everything else on my computer and try again. And yes, it actually worked. It just took the whole day, but it's done. I am now the proud owner of a file as big as 1 GB, storing the world's largest maze in it. Let's take a look at it. The size of the maze is actually insane. It feels like an infinite world. If someone would be trapped here, I don't think that they would ever come out of this maze again. Throughout this project, we implemented multiple maze generation and solving algorithms in both 2D and 3D, built a 3D rendering engine using matrix transformations, created graph visualizers to show the maze structures, and pushed my computer to its limits by generating the biggest maze in the world as massive as a 1 GB image file. Thanks so much for watching all the way to the end. If you enjoyed this video, like and subscribe, and maybe someday I can afford a supercomputer to make even crazier projects. If you have any ideas for what I should try next, drop them in the comments. I would love to see your ideas. Oh, and as a little bonus, I also made Bad Apple, but it's just mazes. Go check it out. Alright, that's it for now. See you in the next video. Bye.